Yeah, so if something is with standard deviation, that's not cool.
Alright.
Yeah, no, if 15 is my wife. They made it. I don't want to so like, it's supposed to use your
Oh.
Oh, I see. Okay, I see. Okay.
Yeah, it's above.
Yeah.
You can find out how
So basically, the opposite of which is none. If I did 1 minus none, I get 1.
exactly, because this is where most of the this is like some 16.
Yeah. Right. Somehow I gave all mine away. I didn't give myself a copy. So the first real question, I'll give you a little example with 3, and that's just to show you the keystrokes and nothing to do with the questions. And then the first real question is 7 successes. So how do I set that up?
44, C, 7, C, 41, 7, 37.
Good. All right. So I like the fact it's a little repetitive, right? It says, okay, you got 44 people. Okay, I want 7 of them to be successes. So of course I want 7 successes. Therefore, I want 37, the rest, failures. So this formula is almost too beautiful. You can see exactly what the hell the whole thing means. And then you just throw all that shit in your calculator. What do you guys get?
11610.
Right? Because it's 16105. So you're going to round it up to 1 because it's a 5. Yep. Okay. And then part B is where I say none, right? And that's the one that came out to that freaky. So I want no successes. I want everybody to fail, which, in my opinion, is good because then nobody's. I mean, is that good? Yeah, good because then nobody's smoking. No, Jeff. 44, thank you. I said it and then I just wrote 0 instead. So what do you get? Now, real quick, now watch. And again, this is not huge. You can do the whole damn formula. How many ways is there to choose nobody from 44? 1 way. What is anything to the 0 power? 1. So then the whole thing really is just dependent on what the hell that is, because these are both 1. So you only have to put that in the calculator if you think about it. If you don't, it's still the same answer. What do you guys get for this? So this is where you get the 7 point blah blah blah. So it's 0.0007. That means that if for any randomly selected group of 44 San Diegans, it's basically impossible to find that none of them smoke. It's not technically impossible, it's basically, but it's very, very unlikely. Right? Tenths, hundreds, thousands, 10,000. 7 out of 10,000 times you will find somebody that, you'll find a group of 44 that nobody smokes. Cool. Okay. And then part C is a very familiar thing, hopefully. At least 1 is 1 minus none. And then 1 minus that is 0.9993. It's got to make sense. It's the opposite. Almost 100% chance you'll find somebody smokes in a group of 44. Maybe. Okay. And then, what was it? Part D says, was there part D, right? What's part D say? Is that where I ask you about the mean?
The
Yeah.
mean is the standard deviation for the number of San Diegans out of 44 who smoke.
Thank you. So then mean is n times p. N was And P was?
0.1.
152. Good. So what do you get when you multiply those together? 6.688. So that's the number you would expect to find. Now here's the thing that was missing before now. In fact, I can't believe I didn't give this example before. So just bear with me. What's the probability if I flip a coin? It hasn't been weighted, just a normal coin. I flip it and I get a head. 50%. What does that mean? Does that mean anything for a single flip of the coin? What's that? If you flip the coin once, it's got to be heads or it's going to be one of them. What the shit does 50% mean then? So percentage probabilities really don't mean anything until you get a large set to look at. The bigger the number of trials you do, the more that becomes something. It's called the law of large numbers. So if you flip a coin 5 times and get nothing but heads, will that really freak you the shit out? Will it? If you flip a coin 5 times, you get 5 heads. Are you gonna like run out the room? Guys, come here. If you flip a coin 1,000 times and you get nothing but heads, that, you know, first thing you gotta ask yourself is, what's your life? You're flipping a coin 1,000 times. You probably should get out the room before that. You know? But that's really good evidence that the coin has been messed with. Why? Well, how many do I expect out of 1,000? How many heads do I expect out of 1,000? 500. Now, to be honest, if you got exactly 500 heads, you would probably be a little freaked out about that too. You expect it to be around 500, don't you? So that's what this is kind of building up to, is I know it should be about 500, but where does unusual start? Is 497 weird? No. Is 480 weird? No. Is 400 weird? Yeah. So somewhere there's got to be some kind of a line we can draw. And to be honest, it's a little bit arbitrary. It has to be. And we're going to make it much more precise when we get to chapter 9. But for right now, we're saying unusual starts 2 standard deviations out. And of course, that's the next step. So just knowing what I expect to have happen isn't good enough to know if something's weird. I also have to know how spread out the occurrences are. Then I can put those together, figure out if it's weird. So what's the standard deviation? What did you guys get for that? 2.381. 5. So 2.382? Yeah. Is that what you guys got? Okay. Did everybody make it that far? All right. And now that last thing I tell you is, this feels a little familiar, right? You put the mean in the middle. But now I'm going up and down 2 steps. Let me show you something. Watch this. So if I do the square root of 44 times 0.152 times 0.848. Bam, right? So there's the, wait a minute, you guys, come on. I'm glad I did that. Nah. This ain't no dominoes bullshit. What's next to the 1? A 4. You don't say the 7 makes a 4 or 5, and then the 5 makes a, no, it's a 4 next to the 1. So what's 1? It doesn't domino effect up. Yeah. Sorry. So, what I want to do, and again, you guys did this, didn't you? I'm going to show you something. If you already did it and you like what you did, great. But watch this. How many of those do I want to go up and down? 2 of those times 2. Ooh, it's amazing. Now watch. This is really cool. See this button right there? I'm going to stow it in X. And now watch what I can do. I want to take the mean minus X and the mean plus X. Are those the numbers you got? Is that your card? Is that right? 1.93 up to 11.45. Do you have to do that? No, but the little stow button is kick-ass. It could come in useful a few times. So this is what we're defining to be usual. Right, so we can do the same thing with the flipping a coin 1,000 times, 500 is the mean, but where does unusual start? Then we know how to find evidence that it's been tampered with if it's outside of the usual area. Are you guys semi with me? This is actually basically getting on the edge of how we test if a drug is effective, how we test all these kind of things. Oh. So would 15 people out of 44 be unusual? Yes, it's out here. It's outside of the usual area. So if I did find 15 out of 44, I might stop and say, where am I? What's in this area? Is there some reason people might smoke more in this area? Okay. Let me see. Was there something else on that? That was the last one, right? Okay, cool. So, on the other side of this, something I don't think we're quite ready for. I want to do this first. Let's do this, and then we maybe call it a day. Because I'm tired. You must be tired. Oh, man. Yeah, well, I'll give this to you in a minute. I'm just going to have to use it. I don't know what happened. I got about more people than I should. All right. So guys, we so the first couple problems we just did a bunch like this. So I mean, probably exactly what's n going to be in this problem? 14. P 0.5 Q 0.5. All right. So like, how would I do exactly 9 heads? What would that look like? The formula. How many times am I flipping the coin? Oh shit, all right, let's do this. 14 is N, 0.5 is P, Q is 0.5. How do I set up the formula? How many times am I flipping it? 14 flips, choose 9 of them to be heads. So how many of these do I want? 9. How many of these do I want? 5. And hopefully somebody out there realizes that when P and Q are 50-50, you can just put 0.5 to the N. Because isn't that 0.5 to the 14th? If that doesn't make sense, it don't matter. Math don't care. It'll come out the right. And you throw that shit in the calculator, you get something. Now if you throw that business in the calculator, if you look down this sheet a little bit, I've got something interesting right here. And this is taken from a table. They rounded to the 3rd place because they're silly. But you can verify that you do get 0.122 something if you do this formula up here. So you see how they read this table? Why does it go from 0 to 14?
N equals 14?
Yeah, because you're going to have 0 up to 14 successes. So let's probably get 9 successes, 0.122. What's the highest probability of success up there? Yes. The highest probability of happening is 7 successes, right? And that makes sense because 7 is the what for this case? If I flip a coin 14 times, how many heads do you expect to show up? 7. So the highest chance of occurrence should be close to, if not equal to, the average. And that hopefully makes some sense. Okay, so how about this one? How would you do this one by hand? At least one head.
14.
Well, help me out. There's one step you want to do.
1 minus.
Yeah, 1 minus probably of 0. So 1 minus 14, choose none, 0.5 to the none, 0.5 to the 14th. And that's going to be something like, you know, 0.99999 something. What do you got? Anybody got it? No. Is everybody cool with what I wrote down up there? At least one head is 1 minus the probability of no heads. Because I don't want to do at least one head. That would mean I have to do the formula for 1, for 2, for 3. That's what at least 1 means, up to freaking 14. I don't want to do that formula that many times. I don't want to. So I'm going to do it 1 minus the opposite, because I just have to do one formula then. What do you guys get? Anybody?
999938.
All right. Okay. I think it's a 3. I crowdsourced it. Is that right?
99993.
Okay. Cool. 99993. Okay. All right. Were you expecting more? That's it. That's that answer. That problem's done. Okay. Now, the slightly more interesting thing is when you start to figure out what is unusual or not. This is like I was just talking about with 1,000 flips. So sure enough, if you flip the coin 14 times and you got nothing but, even if you got, nothing but tails, that is so unlikely to happen. If you got 0 heads, look what even the table says. It's basically 0. 0 plus in that table meant it was just barely above 0. So that is so unlikely that it would be evidence that something's wrong with that coin. Is it proof that something's wrong with that coin? No, because there's still a possibility it could happen, right? I like it. Okay. So what does the mean? We already figured it out. 14 times 0.5 is 7. That's amazing. So I expect around 7 heads. What's the standard deviation?
1.871.
Do it again, sorry.
1.871.
1.871? Is that cool? You guys all right? You guys can double check that. So then where does unusual start? If I do 7 minus 2 of these, you get about, what, Jeff? 3.3, roughly?
3.3, yeah.
And so what's the maximum usual value would be?
10.7.
10.7 probably. So even if you got 11 heads out of 14 flips, that officially would be considered unusual. 11 could be evidence that this has been tampered with. 12 would be stronger evidence. 13 would be even stronger evidence, and so forth. So this is starting to sound a little bit like a court case, right? You can have some evidence, sort of evidence, stronger evidence, really strong evidence, but never any proof. You cannot, unfortunately, you can't prove almost anything, really. If the sun will come up, who knows? Who knows if the sun will come up? Oh, kids, that's so bleak. All right. So what I've done down here, so this is all kind of review of chapter 4. The purpose of this handout is to get us thinking correctly for the next chapter, because we are approaching the most important chapter, which is chapter 6. Chapter 6 is the most important chapter. All right. So watch this. This gets interesting. Can anybody tell me what the total area is of this little Mayan pyramid thing?
1.
Yeah, it's got to be 1 because it would just be adding up all the probabilities, right? Anytime I have got a probability distribution where the total area is 1, the probability of any event in it is equal to the area of that event. So, for example, what's the area of the rectangle that 6 defines? How tall is this rectangle? No, 6. 0.183. How wide is it? 1. So what's the area of it? 0.183. Now that is boring. I understand. It's like, I already knew this. 0.183. Right? But the connection we're starting to try to make here is that probability is connected to area if I make the total area 1, because then that matches up to the total probability being 1. So, does anyone play darts? Is that the appropriate way to say that? Like, you don't say play bowling, you say bowling. Anybody play dart? Anybody just threw a dart before a dartboard? Ever? All right, if you come on, you do that and your friend just walks by and you get him in the head, whatever. All right, it sounds like somebody's done that. I've done that. I've been on both sides of that. Yeah, it helps if you have a little bit of something in you and you don't feel much. Sir, what? What? Oh, shit. So, not going to get into any real specifics. Here's the dartboard. What's right in the middle? No, it's not. It's not the tiny things, man. Yeah, right? This is the bullseye. And then there's the, like, pie chunks here, right? Okay, all the way around. So, if I had somebody throwing darts at this board, and I only counted the ones that hit the board, right? Not hit here, or hit people walking by. They have to hit the board. Are you with me? So what's the probability that there's a dart that I count if you throw some darts and some hit the board? 100%. Somebody's going to hit the board. All right. What's the probability that the dart lands here if they're just kind of throwing them without really trying? It would be equal to the area of this. It would be the percentage of that board that area occupies. Why is it so hard to get it here? Because it's a very small area. So the probability of getting it in that bullseye, if you're just kind of randomly throwing it, is equal to the area of the bullseye. If I make the whole area 1. So that's a way you can gauge somebody's effectiveness at playing darts, whatever the hell you say. If somebody gets it in the bullseye when they're trying to on purpose, much more often than I would predict they would, that's evidence that they're a good dart player. However the hell you say it. You with me? Not lawn darts. Those have been outlawed. What a great idea. Let's arm kids in the backyard. Anyway, sorry. So, here's the ultimate place we're headed to. We're not going to finish this whole little worksheet right now. We're going to do some of it later. There is a category of probability distribution. Well, there's a type. We've done discrete probability distributions. Believe it or not, I didn't use that word before, but a binomial. What's the number of successes? You could have 0 or 1 or, oh shit, that's discrete, ain't it? Because it's skipping a bunch of shit. If I had a distribution that dealt with the amount of time I had to wait for the next bus to show up, that's not discrete, right? So there's a type of continuous distribution that's called uniform. What do you think when I say the word uniform?
It's all the same?
All the same, right? Like the word uniform, like somebody wearing a uniform. So everybody's got the same thing. So uniform distribution means all the probabilities are the same. There's no higher peak or lower peak. So bus times. If I get to a bus stop, I could have to wait 0 minutes, right? Let's pretend like we're in a city where the buses run on schedule. I could get there right when the bus is there, right before they're leaving, so I had to wait 0 minutes, right? Or I could get there right when they're pulling up, so I had to wait 5 seconds or something, or even 5.78246639. Up to, let's say they come every 20 minutes. Right? Maybe? I don't know. It's been a while since I had the right bus thing. Yeah, this is true too. Let's just pretend like we're in Germany. There we go. I was in Germany, man. That train was like there. You could set your clock. In Italy, it's like it's only an hour late. So, what the shit? So here's what it would look like. Uniform distribution would look like this. So no time has more probability than any other time. So if the bus comes every 20 minutes and I arrive there at some random time between the two, I could have to wait anywhere from 0 to 20 evenly. There's no reason I should have to wait 10 minutes more often than something else. Okay, so everybody's starting mind with me. That's what uniform means. How do I make the area of this 1? If I can make the area of this 1, any question about, well, what's the probability you would have to wait more than 15 minutes? Or what's the probability? Any of those questions would be easy, because it's just going to be finding the freaking area, which is finding the area of a rectangle. It's easy as shit. How do I make that area 1? How tall do I want this to be if the area is going to be 1? Okay, how'd you get that?
It's like 20 times x is equal 1.
Yes. So what's the length of this? 20. The height I don't know, but I want the area to be 1. So like you just did, 20 times I don't know equals 1. So the height is 1/20. And you can make that 0.05. I like it. You guys with me? So it's basically 1 divided by the length. That kind of makes sense. What do you multiply a number by to make it 1? You multiply by its reciprocal, right? Okay, I like it. So for example, now if I ask you what's probably, I have to wait between 5 and 11 minutes, can you draw that in here? Do it. Do it. Try it. Come on. Sorry, I'm getting loopy, man. I'm getting loopy? Be quiet. Okay, have you guys, so like here, 5 to 11. Doesn't even have to be perfect, don't trade off. So what, can you shade in the area that's the answer to the question? Yes, it's this area. Bam, 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 right? What area is that? And then I'm done. That's uniform distribution. That's almost too nice to believe. It's so easy, but it happens so infrequently. So there's a bit of a trade-off. What's the area of this? How wide is it? How? 6. And how tall is it? Everything's 1/20th in this thing, right? So it's going to be 6 times 1/20th, which comes out to be 30% if you do it, right? You guys with me? Sometimes students are like, no, let me make that hard because this is supposed to be hard, right? But again, the hardest part about a uniform curve, very often, uniform distribution is the height. Let me ask you, here's a funky question. What's the probability x is greater than 21? Zero. Can't happen. We're assuming this is true. That's it. The way this represents it is it goes to 0 chance out there. This is the only stuff that could happen. So that's 0. What's the probability x is greater than, what do you got, Jeff? Greater than 0? 100%. I like it. What's the probability that x equals 10? Uh-oh. This is definitely the weirdest one. Somebody knows. Remind me, the answer is equal to the what of the thing? The area of the thing. So the probability x equals 10. Here's 10. Here's x equal to 10. What's the area of a line? No. 1 would be the area between 10 and 11. I'm talking about this. How thick is a line? Not. Right? Now we can get into some interesting shit like the idea of Iota, which is, my fellow mathematicians across the world don't like this, but it's basically the smallest positive number, is one way to look at it. It's sort of like infinity is the largest positive number, which doesn't exist. It's a process. Are you guys semi with me? Anyway, sorry. For humans, for non-mathematical types, the answer to anything that equals something is 0. How many total numbers are there between 0 and 20? Don't say 20. Infinite. So what's the denominator going to be for any specific situation here? Infinity. What's anything divided by infinity? 0. So the probability I get exactly 10 out of an infinite number of choices is 0. No? So just remember, I don't have to get into infinity. I don't have to do any of this shit. It's the area, and the area of a line is 0. That's really where you should go. If you're more interested in some more interesting stuff, you got iota in there, you got infinities in there, you got all this other shit. But it's not really necessary because it's equal to the area, and the area of a line is 0. Or close enough to 0 for everyday use. That's the one thing that's a little weird about this, is that. But it's because this is continuous, which means it has an infinite number of values possible. So any specific value is almost... Find me somebody who's exactly 5 foot tall. You cannot do it. Because I can get them... We have measurement devices that will measure, and I'm telling you, by the 8th decimal place, they ain't at 0 anymore. It ain't 5.00 forever. Do you guys see what I'm saying? You start to see how it is basically impossible to get exactly something. Yes, maybe, no, maybe, yes. All right, that's enough. Let's get out of here. Tomorrow we got that quiz, the double quiz. Who's this? Is this Rafi or Rafi? Who else has my calculators? Thank you. Chapter 3. Just probability, yeah.
What double quiz?
Huh?
What do you mean double quiz?